are some macroscopic characteristics of gases. So you probably already know most of these. Gases can be compressed, right? So they can be compressed, and they're also going to expand to fill their container. Oops, there we go. They can be compressed, they can expand to fill their container. Gases also have low density. So if you remember from chapter 3, we're looking at density. We know that density is just mass over volume. Mass over volume. So if we say that they have low density, that means they have not a lot of mass, but a whole lot of volume. So you have like lots of volume. That's going to give you a small number. When you take a small number divided by a big number, you're going to end up with a really small number. So gases are not very dense. You can mix gases. Air is just a mixture of gases. So gases like to mix. And then gases are going to exert a certain amount of pressure on the walls of their container. So they're going to exert some pressure here on the wall. So we're going to talk a lot about gas pressure. We're going to measure it, and we will be able to convert it from one unit to another. So we'll practice our dimensional analysis. So the ideal gas model is basically saying there's 5 points to it. The first point is saying that gases consist of molecules. They're moving. They're in constant random motion. Gases are crazy. They're just moving all the time. And the molecules are going to collide with each other. They'll hit each other, and they'll hit the walls of the container. But as long as you don't change the temperature, the average kinetic energy is going to stay the same. So that they will collide and hit each other and hit the walls of the container without the loss of total kinetic energy. We'll talk more about kinetic energy later on in this chapter. Gas molecules are spread out. They're really widely spread, so they're really far from each other. And the actual volume of the molecule is negligible when you're talking about how big the container is. So if you, for example, if you had suppose you had this container, right, and it's full of gas molecules. Suppose it's a 1 liter container. We would say that each one of those molecules, like this molecule, has the entire 1 liter of space to move around in, even though the gas molecules themselves are actually taking up some space. We'll just assume that the molecules are actually really, really, really small compared to how big of a container they have. So each one of those molecules has the entire liter to move around in. And then the last part, is saying that the gas molecules behave as independent particles. So they don't really see each other. They're not attracted to each other. They're not really. They don't really repel each other either. That the attractive forces between them are negligible. So the molecules are really, so just to summarize, gas molecules are moving really, really fast. They're really far apart from each other. They don't really see each other. They can hit each other, but then they don't lose any of their kinetic energy. So let's see, now we can talk a little bit more about gas measurements. How do we measure the pressure of gases and all these sorts of things? So we're going to use a barometer. Usually a barometer here is used to measure pressure. The first barometer was a mercury barometer made by Torricelli, a nice Italian guy named Torricelli. You probably never heard of him, but you may have heard of Galileo. And Torricelli was a student of Galileo, so he's pretty cool. Torricelli also has his own unit of pressure. Down here, this is the torr. Torr is named for Torricelli. And what he did was he made this barometer over here. This is a barometer. So this is all mercury. So you take a pool of mercury, and then he took an evacuated tube. So that just means it has nothing in it. It's evacuated. There's no air. It's just a vacuum. And he took that tube and he kind of put it upside down, and he noticed that it kind of acted like a straw or like a vacuum. It just sucked up a certain amount of mercury. And he measured the height of that mercury. So that says PHG, that HG is mercury. So he just measured the height of that column of mercury. He said, all right. And he noticed that it changed. It wasn't constant. It depended on, he took it up on a mountain and he saw it change. And at sea level or below sea level, it was changing. And so how this thing really works, or how does this measure the atmospheric pressure? So the atmosphere is exerting a certain amount of pressure on this pool of mercury. And depending on what that pressure is, this column of mercury is going to change. So that column of mercury will change depending on what the pressure is. So BHD, that's the HD is the symbol for mercury. So whenever you see that, that's just mercury there. So some pressure units, millimeters of mercury. So mmHg, that's millimeters of mercury. You'll see that a lot. It's the same as a torr. Torr millimeters of mercury are the same unit. And what we're going to use a lot more is the atmosphere. So 1 atmosphere is 760 torr, 760 millimeters of mercury. You don't have to memorize that. I'll give that to you because that's just a conversion factor. Remember, conversion factors from chapter 3. Here's some more that might help you when you're doing the homework, assuming you're going to do the homework. You have a Pascal, kilopascals. 1 atmosphere here, these are all going back to atmosphere. So 1 atmosphere is 14.69 psi. You may have heard that before when you're measuring the pressure of your air, the air in your tires. What else do we have? We don't. Yeah, we might. Yeah, so pounds per square inch. That's what psi is. So let's try one really quick conversion. Let's see if we can take the pressure here inside a steam boiler is 11. Here we go. 1154 psi, and we want to convert it to atmospheres. So we'll see if we have a conversion factor. We definitely want psi on the bottom, pounds per square inch on the bottom, and we're trying to go to atmosphere. So we'll go up there. There's our conversion factor right here still. It's on the screen. So 1 atmosphere is 14. So I'm going to put atmosphere on top because that's where I'm trying to go. 1 atmosphere on top, and 14.69 psi on the bottom. 14.69. So remember, whatever unit you're starting with, that's what you want on the bottom, and on the top is where you're trying to go. And so my psi units cancel. I'm going to end up with something in atmospheres. And when you work that out, you get 78.56. Okay, 78.56 ATM.